Hey everybody, welcome back. This is Ripley. Today we're going to talk about section 9.5, the dot product. Now, the dot product is a way of combining vectors, but you got to sort of understand what this is really all about. I'm going to show you, I'm going to use an applet from the internet to show you what the dot product is, literally, here in just a sec, and then I'm going to show you the rules and kind of some cool theorems that we get to use. All right, first things first. If I take a vector, all right, and I'm going to call this vector v, and then I take another vector that's not parallel to this vector, all right, so they're in different directions, and I dot this thing. So let's call this thing w. All right, now I'm going to change my colors. If I take the horizontal component of w, remember, w can be written as the sum of a horizontal and a vertical component. All vectors can be written as the sum as a horizontal and vertical component. And remember, w can either be written as, you write it like a, b, or it can also be written as ai plus bj, as can v. V can be written as well, in this case, it's strictly a horizontal, right? Because it's vertical is nothing, but I could do this as like a1, b1, and then I can write this as a1i plus b1j. Now, what the dot product is you take the product. It's simply a number. It's a scalar. It's not a vector. I take the product of the magnitude of the horizontal component of w, if I'm going to go w dot v, and then I take the magnitude of, let's change colors, then I take the magnitude of v, all right, and I multiply those two values together. Then I get w dot. This is a dot. It's not times, but it's sort of the vector equivalent of timesing. Now this gets really useful. The most common problem that we do is a problem like if we've got a wagon on wheels and we've got a handle right here, right? And we're lifting up at an angle of, I don't know, 35 degrees, right? If I got 35 degrees and I'm exerting a force on this handle, and I want to figure out how much work it takes to drag this wagon a certain distance. Well, what you end up with is you end up with a distance vector, and then you end up with, if you think about it, you end up with a force vector that you're exerting on the handle of the wagon. Now that force vector can be written as the sum of the horizontal component and the vertical component. Now the vertical component does nothing to add to the work done. That's the force that is lifting the wagon up, but it's not dragging the wagon forward at all. So in this case, we would have a force vector, which would just be this, whatever this vector is, let's call this v and let's call this d, right? And it would be v dotted with d. That's how we would write it. Now, you may be saying, wait a sec, but why do we have to worry about the entirety of v? Well, by definition, the way that the dot product works is it's really the projection of the parallel part of v, which in this case happens to be the horizontal part. All right? Now, enough theoretical. Let's actually go to an applet where you can sort of see how this works out. Check this out. This is a pretty cool applet. I'm going to reduce that sucker. All right, check this out. I'm going to keep it simple for you first. Watch this. I'm going to make beta. I want this guy to be B over here. You see this over here? I want this guy's size to be 1. Sometimes this thing's a little bit finicky. Okay, so B is 1, 0. So this is our origin right here. And then here's A. Now watch what goes on here. All right, what I have, see this yellow line? This yellow line is the projection of the horizontal part of red, the horizontal component, and it's written down here. Okay, and then I don't even care about the vertical part. Okay, so these are all written over here. B is written as 1, 0. A is 0.56, 0.91, and these are the amplitudes of both. All right, the dot A dot B is this horizontal part, which notice is 0.56, times B, which is 1. So it should be 0.56. Now, watch what happens. If I stretch this guy out a little bit, let's go 1.51, now notice what happens. Well, B's magnitude is 1.51, right? A cos theta, as you can probably figure out, is that's where we're getting this horizontal component from, is 0.566. If I multiply 1.51 times 0.566, I get 0.855. And as I move this guy around, watch what happens. I get closer. See that horizontal, that yellow part grow? Now notice how green just got really big. That's 0.1. I want that thing to be 0. There we go, like that. Watch the green on the bottom really grow as we get longer. It's because I'm taking B, which is 1.49, and then A cos theta, which is the horizontal projection, is 1.83. And if I get 1.49 times 1.83, I get 2.727, which is pretty cool. Now, you may say, okay, Ripley, what if my vectors aren't horizontal? In other words, what if this B guy isn't horizontal? That's a great question. We'll watch what happens. It's almost as though I just rotate the whole system. Well, what is this yellow part, you may say? It is the parallel component to B. It's the projection of the parallel component of A onto B. Then you take the magnitude of that, which is A cos theta, 1.33 or 1.344, times the magnitude of B. All right, now, believe it or not, watch this. This part's really cool too. Let's keep it simple, put it here. Now, think about this. What happens if my vector goes the other way? What if it goes back here? I don't want you to look. Check it out. Look at that. Now what happens? Well, my dot becomes negative, doesn't it? It has to, because the horizontal component of the red, right, is negative, and the product of negative 0.35 and 1.75 is negative 0.613. Which is pretty darn cool. They rounded, of course. Okay? Okay, now, hopefully that helps you figure some stuff out as far as what we're about to do. The irony is this way of thinking about a dot product, while it's very helpful visually, computationally, it's not as helpful. Because actually, it's really easy to dot two vectors. I got to get rid of avocado green, don't I? That's obnoxious. If I have a vector v, and I'm going to call this AB, which is exactly the same as AI plus BJ, right? They can be written that way. And I have a vector W, and let's call this A1, B1, or A1I plus B1J. Watch how simple it is to dot them. V dot W is simply equal to A times A1 plus B times B1. Notice the I and the J disappear. They disappear. It's a scalar. Remember, this is a magnitude that we're finding. So you simply take the product of the horizontal components of both and you add it to the product of the vertical components of both.